I'm Drew Baglino, SVP of Powertrain and Energy Engineering at Tesla, and I'm incredibly excited to talk about what we've been doing at batteries here at Tesla.
That wind and solar comprise 75% of new electricity capacity in the US this year. Now, it's also worth noting that the length of time that power plants last is on the order of 25 years. So even if 100% of energy generation was sustainable, it would still take 25 years to convert the grid. And it's also worth noting that in the past 10 years, power production from coal has dropped in half. So it went from 46% of electricity in 2010 to 23% in 2020. So in terms of Tesla's contribution, we've delivered over 1 million electric vehicles, 26 billion electric miles driven, and many gigawatt hours of stationary batteries, 17 terawatt hours of solar generated. So solar is sometimes underweighted at Tesla, but it is a massive part of our future. The three parts of a sustainable energy future are sustainable energy generation, storage, and electric vehicles. We intend to play a significant role in all three. So to accelerate the transition to sustainable energy, we must produce more EVs that need to be affordable and a lot more energy storage while building factories faster and with far less investment. Goal number one is a terawatt-hour scale battery production. Tera is the new giga, and a terawatt is 1,000 times more than a gigawatt. We used to talk in terms of gigawatts. In the future, we'll be talking in terms of terawatt hours. So this is what's needed in order to transition the world to sustainability. You basically need on the order of roughly 10 terawatt hours a year of battery production to transition the global fleet of vehicles to electric.
And the average vehicle lasts 15 years, so we're talking about 150 terawatt hours, give or take, to transition the whole all vehicles of all types to electric. And then on the grid side, we have a similar mountain to climb, 1,600 times growth from today's grid batteries to go 100% renewable on the grid and to take all of the existing heating fossil fuel uses in homes and businesses 100% electric.
Yeah, and this number, I think, might grow even more, as the world economy matures and as countries with high populations industrialize, we could see this number be even more. But let's say it's like roughly 20 to 25 terawatt hours per year, sustained for 15 to 25 years to transition the world to renewable. So today's batteries cannot scale fast enough. They're just too small. For Giga Nevada, 150 gigawatt hours per year is like what we probably expect to make out of there. But this is really pretty small in the grand scheme of things. That's only 0.15 terawatt hours.
We would need 135 fully built out Nevada gigafactories to achieve 20 terawatt hours a year. It's not scalable enough of a solution. We need a dramatic rethink of the cell manufacturing system to scale as fast as we can and should.
So, and then goal two, obviously, we need to make more affordable cars. I think one of the things that troubles me the most is that we don't yet have a truly affordable car, and that is something that we will make in the future. But in order to do that, we've got to get the cost of batteries down. We've got to make, and we've got to be better at manufacturing, and we need to do something about this curve. The curve of the cost per kilowatt hour of batteries is not improving fast enough. EV market share is growing, but EVs, still aren't accessible to all. That's why we've got Battery Day.
We have a plan to halve the cost per kilowatt hour. And we're going to go through that plan with you today, step by step, and build up how we get to these goals.
I mean, we basically thought through every element of the battery, well, almost every element. There are a few more elements that we won't get to today, but we will get to in the future.
But let's talk about what is in a battery cell. We've got the cap and the can, negative and positive terminals of the cell. When you open that cell, you've got a tab connected to those terminals, what we call the jelly roll, which is the wound electrodes on the inside. You can actually see what this looks like as you unwind it. This is over 1 meter long in a typical 2170 cell. And then, to explain what's actually going on here, we've identified we've got anode, cathode, separator, positive and negative terminal. Watch what happens as we discharge the cell. Got lithium moving from anode to cathode, and then the reverse when we charge the cell. anode moving from lithium moving from cathode to anode across the separator. This is the basic of what makes all lithium-ion batteries, whether they're no matter what the form factor is. And when we look at what's happened to date, at least in our products, we've moved from the 18650 form factor to the 2170 form factor through great collaboration with our partners, Panasonic, new partners like LG and CATL, and probably others in the future. Yeah. We need to go beyond just what we're looking at us in front of us, and study the full spectrum of options. So as you can see, we kind of swept the key figures of merit, how much we can reduce the cost, and how much vehicle range increases as we change the outer diameter of the cell. We found a sweet spot somewhere around 46 millimeters. But it's not just about a bigger form factor. Like, anybody could make a bigger form factor. There are problems as you make cells larger. In fact, supercharging and thermals in general become really challenging as you make bigger cells. And this was the challenge that our team set our sights on to overcome. And we did. We came up with this tabless architecture that maybe you've heard about, that basically removes the thermal problem from the equation and allows us to go to the absolute lowest cost form factor and the simplest manufacturing process. We basically took the existing foils, laser patterned them, and enabled dozens of connections into the active material through this shingled spiral you can see, with simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits. And so when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase, just form factor alone.
The actual production plants will be more on the order of, maybe 200 gigawatt hours, maybe more over time.
So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. And now that you've been teased on this factory, we're going to go on and walk step by step through that factory and discuss a series of innovations there. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. We were able to get to the point where we can implement assembly lines, one line, 20 gigawatt hours, 7 times increase in output per line. And when you're thinking about scalability and pure effort, having one line be 7x the capability is just effort multiplying.
Yeah.
86% reduction in formation investment, 75% reduction in footprint.
What this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour or gigawatt hour. It's just basically 4 times better than the current state of the art to the best of our knowledge.
You know, as Elon said, we're going to try to even improve on this as we push towards our goals, which are...
This is just talking about Tesla internal cell production. As I tweeted out earlier, we will continue to use our cell suppliers, Panasonic and LG and CATL. And so this is 100 gigawatt hours supplemental to what we buy from suppliers.
And not only is all of that manufacturing innovation fantastic for enabling scale, it's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level. Start with raw metallurgical silicon, stabilize the surface with an elastic ion conducting polymer coating that is applied through a very scalable approach. No like chemical vapor deposition, no highly engineered high capex solutions, and then integrated into the electrode through a robust network formed out of a highly elastic binder. And in the end, by leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement. Yeah, and when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level. And that's what we've been working on with our high nickel cathode development, which has 0 cobalt in it. Leveraging novel coatings and dopants, we can get a 15% reduction in cathode dollar per kilowatt hour. 35% of the cathode dollar per kilowatt hour is just in transferring it into its final form. It's a 66% reduction in capex investment, a 76% reduction in process cost, and 0 wastewater. Much more scalable solution. Yeah. And just doing that, just localizing our cathode supply chain and production, we can reduce miles traveled by all the materials that end up in the cathode by 80%, which is huge for cost. The way the lithium ends up in the cell is through the cathode, so then we should obviously on-site lithium conversion as well, which is what we will do using a new process that we're going to pioneer. That's a sulfate-free process again, skip the intermediate. 33% reduction in lithium cost, 100% electric facility co-located with the cathode plant. And eventually, as we said at the beginning, when we get to this steady state 20 terawatt hours per year of production, we will transfer the entire non-renewable fleet of both power plants, home heating and battery and industry heating and vehicles to electric. And at that point, we have an awesome resource in those batteries to recycle to make new batteries. So we don't need to do any more mining at that point, and you can see why. And just to think about what this actually means, the recycling resource is always 10 or greater years delayed because batteries last a really long time. But all of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level.
So it starts with having a single piece casting, or a single piece casting for the front body and the rear body. And in order to do this, we commissioned the largest casting machine that has ever been made. And it's currently working just over the road at our Freemont plant.
And in addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah. Now, to be clear, it will take us probably a year to 18 months to start realizing these advantages, and probably to fully realize the advantages, probably it's about 3 years or thereabouts. All right, well, I guess thank you everyone for coming. I hope you liked the presentation. Thank you.
Thank you.